thermodynamics. First law of thermodynamics. So, ladies and gentlemen, yesterday we talked about how we can measure or actually calculate the internal energy of a sample of gas. And recall the formula U equals 3/2 N R T. Going live. What is the first law of thermodynamics? Well, recall, if you know the number of moles and the temperature of a gas, you can calculate the internal energy. So the question is, how could we increase that internal energy? If we want to increase that internal energy, there's two main ways. Let me make some room on this page. One, you want to increase the internal energy? Put a Bunsen burner underneath that gas sample. Add heat. If you add heat to the sample, that would increase the kinetic energy, which would ultimately increase the internal energy. So, add heat to the gas. Remember, heat has the symbol Q. By adding heat, you would increase the temperature, and of course when the temperature goes up, the internal energy increases. The second way is to do work on the gas. If you were to come over here and push down on that piston, that would require work. And by squeezing those suckers down, that would actually increase the average kinetic energy, temperature would go up, and there would be an increase in the overall internal energy. So, second way, do work on the gas. You want to get really wild? You can add heat while you simultaneously do work and push down the piston at the same time. That would really increase the internal energy. Oh, those are good times, huh? Now, basically, folks, we could say all of this with one mathematical formula, which is known as the first law of thermodynamics. And basically, that formula says if you want to increase the internal energy, the change in the internal energy, or the amount that it increases, is equal to however much heat you add to the gas plus however much work you do to the gas. That formula is known as the first law of thermodynamics. And basically, folks, it's a version of the work energy theorem, you know. It's a pretty simple formula. Let's look at some, like easy numbers. Example. Let's say 35 joules of heat is added to the gas while 20 joules of work is done pushing down the piston. What is the increase in internal energy? Well, we know that the change in internal energy equals the amount of heat done, the amount of heat added to the gas plus the amount of work done on the gas. So the change in internal energy would equal 35 joules of heat added plus 20 joules of work done on the gas when the piston was pushed down. So the change in the internal energy would equal 55 joules. The only time this formula is a little tricky is when you're deciding whether the values are positive or negative. So I just want to get this straight right from the start, because if you can get it straight right from the start, it's not really a problem. But it's very, very important to focus on whether the values of delta U, Q, and W are positive or negative. The heat is positive when it's added to the gas. On the other hand, if you have a gas sample that's giving off heat, maybe it's at a high temperature to begin with, and maybe it's a glass container, and it's actually cooling down, it's giving off of the heat, then the Q would be negative. Said when the heat is released from the gas, always looking for a key word there, like when the heat is expelled from the gas, or when the heat is extracted from the gas. The heat goes from the gas to its surroundings. So if the heat is going in, that's positive. But if the heat is coming out, that's negative. Now work. Work is positive W is positive when work is done on the gas. In other words, the piston is going to be pushed down. That movable top, I'm calling that the piston, has to be pushed down. W is negative when work is done by the gas. Oopsie. In other words, the movable piston on top is pushed up. So if you go up to the gas sample and you push down on that piston and you push it lower, you just did work on the gas, and the work is positive. On the other hand, if the gas does the work, and if the gas uses its gas muscles and pushes the piston up, yes? Well, when the gas pushes the piston up, that's considered work done by the gas. And in our first law of thermodynamics, this term right here, that work would be negative. So it's a little bit tricky because work is positive when work is done, the W is positive when work is done on the gas. Work is negative when work is done by the gas. That one little two-letter word, on or by, makes all the difference. So you have to closely read the question. Is the work being done on the gas, piston being pushed down, or by the gas? The gas is pushing the piston up. So we talked about the heat, we talked about the work. Now let's talk about the change in internal energy. Recall, U equals 3/2 nRT. Well, if there's an increase in the internal energy, the increase in the internal energy is going to be equal to 3/2 nR delta T. However much the T changes, that's how much the U is going to change. If you have an increase in temperature, you're going to have an increase in internal energy. So, delta U is positive when the temperature of the gas goes up, or I should just say increases. And of course, delta U would be negative. When temp decreases. And this all can be seen from this formula right here. So, what we're going to focus on now is this work term right here. How do you calculate how much work is done on the gas? One thing I think I failed to mention, with that work, and we should probably note it right here. You might just want to add this to your notes, just a bit back. If the work is positive, what does the volume do? Don't shout it out. Take a moment to look at it. Fill in that blank. And on the contrary, if the work is negative, what does the volume do? This is the clear-cut way of deciding whether or not the work is positive or negative. Just check out the volume. And of course, if the volume doesn't change, there isn't any work being done. So Ryan, up on top, if the work is positive, what happened to the volume? Did it increase or decrease? Decreases. Yes. And if the work is negative, the volume increases. All right, let's take a 2 o'clock stretch and we'll come back and we'll calculate the work. How can the work done on a gas be calculated? Yeah, this is probably going to be the next lesson. How can the work done on a gas be calculated? Now, if you push down on that piston with a force F, and the piston drops down a distance delta x, if you want to know how much work you did, the work done simply equals the amount of force used times the distance that the piston was pushed down. Recall, pressure is equal to force divided by area. So if you solve this for force, the force that you push down on that piston with is equal to the pressure exerted on the piston times the cross-sectional area. This area right here. So instead of saying, oh, I did so much work, and taking the force times the distance you push it down, we could rewrite that formula. Work is equal to, instead of writing force right here, we're going to replace it with pressure times the area. Times the distance that the piston is pushed down. let me remind you with baby numbers, if you have, actually, no, not here, not here. If we just take a closer look, this area times the distance it's pushed down, that has a physical significance if you're looking at the gas there. Look, this area right here. Of course, that's the area underneath the bottom there too, right? That area of the top chamber holding the gas times this distance, which you can almost think of as the height. What is that area times that height? That's the volume. Yes? That's a volume. If that piston gets dropped down to here, if the piston moves down to here, this volume right in here is going to be equal to the change in volume of the chamber. It's how much the volume changes. If you take the final volume and you subtract the initial volume, the change in volume would be this little piece right in here. So this area along the top times the distance you push down the piston, that's the change in volume. So the new look of the work formula becomes pressure times the change in volume. But we have a little problem that we have to take care of. Do you have a comment, Ryan?
So it's pressure exerted on the gas.
Yeah. Now, if it's moved down at a constant velocity, the pressure exerted on the gas would be equal to the pressure that the gas exerts on the bottom of the chamber. So they would actually be one and the same. So in other words, if you do it in a smooth, uniform fashion. I'm actually impressed that you kind of picked up on that, because I kind of glossed over that. I start off talking about the force and the pressure pushed down on the top of the piston, but ultimately when we use this formula, that pressure right there is the pressure inside the gas. And you kind of caught me on that. And believe it or not, if it's pushed down at a constant velocity, then the pressure exerted on top is going to be equal to the pressure from the gas below. Because if they weren't equal pressures, they wouldn't be equal forces. And if they weren't equal forces, it would be accelerating. So if you're doing it uniformly. So yes, that P originally started off as the pressure on the gas, but that's the same as the pressure that the gas exerts up on the chamber.
Right.
That's an interesting point. With the pressure, you don't have to worry about whether it's positive or negative. I think it's just going to be like positive. But we have a little final glitch that we have to take care of. Well, the piston is pushed down the work is blank and the change in volume, which equals the final volume minus the initial volume, is blank. So if the piston is pushed down, recall, did we define that as positive work or as negative work? Did? Positive. But if it's pushed down to here, how is the new volume, which you could call the final volume, how is that going to compare to the initial volume? Dave? It's less. And since the final volume is going to be less than the initial volume, is the change in volume going to be positive or negative? It's going to be negative. So the problem is, if we push that piston down, this term right here, delta V, would be negative. But what do we want the work to come out as? If you push the piston down, you want the work to come out positive. So we actually have to tweak the formula so that it works with our plus-minus business. So basically, the formula has to become W equals P times negative delta V. But most people just end up putting the negative out front. And it becomes W equals negative P times delta V. So this is the new look of our work formula. You can kind of recognize force times distance. It's in there, but now it's pressure times volume. Now, this next bit of business is very unfortunate, especially when you're first learning physics. It's nice if everybody does things the same way. But there's actually two different ways, there's two popular ways of setting up the sign convention. The way I just taught you right now, where the work is positive when the piston is pushed down, that's what the College Board convention is. That's how it's done on the AP exam. That's how you have to report your answers on the AP exam. So that's how we're always going to do it. We're going to practice that way. However, in your textbook, they use the opposite plus-minus system. The textbook says if the gas pushes up on the piston, that's positive work. So when we say the work is positive, the textbook would call it negative. When we say the work is negative, the textbook would call it positive. So anytime you're checking answers in the back of the textbook, your internal energy answers, they're going to be exactly the same. Your heat answers, they're going to be exactly the same. But whatever you get for your work answer, they should get the same answer with the opposite sign. Now, since the textbook is using the opposite work convention, their formulas look a little different. And I want you to always practice by using the formulas the way I present it here. So let me do a side-by-side comparison.
Are all the business beginners teaching
none of this internal energy business, this whole unit, none of it is on the Regency, nor is any fluids. So, where we have the increase in internal energy is equal to Q plus W. If they have the opposite sign convention in the textbook, the way they have to write the formula is delta U equals Q minus W. That's perfectly fine if you're going to stick with that convention, but we're going to stick with the AP convention. When we write the work formula equals the negative of the pressure times the change in volume. The textbook doesn't have that negative problem. The textbook work formula is pressure times change in volume. So keep that in mind if you're ever looking at any of the sample problems. The textbook is using the opposite sign convention, S-I-G-N, when it comes to work. Sorry about that. Okay, so in summary, first law of thermodynamics. You want to increase the internal energy? You can either add heat or do work, or get wild and crazy, do both. Hey, what are you doing this Friday? You want to add some heat and do work on the gas sandwich at the same time?
Roger.